we first have to look at a definition of the word optimize. This is a word you may have used at some point. For some of you, it just sounds like something from Transformers. So optimization is the process of finding values that make a quantity the greatest or the least possible. And usually you're given certain conditions. So an example, a certain company is being asked to make a cereal box and they're given so much surface area, but they need to somehow maximize the volume. There's a bunch of different shapes that we could choose to make for that cereal box. One shape would use the least surface area possible while still getting the most volume possible. Obviously, material costs money, so it would be best to use the least material, but somehow get the most space. What we're going to do in this video is we're going to look at perimeter and area. So we're going to try to maximize area. We'll do that by looking at a couple of examples. So the first example here says find the dimensions of fencing that will maximize the rectangular area of an enclosure with a fixed perimeter of 32 meters. So if we go back to our definition of optimization, given certain conditions, so in this case we're given a fixed perimeter of 32 meters, and we want to make something the greatest possible. In this case, we want to make area the greatest possible. I'm going to start by thinking about one set of dimensions, so a length and a width, that would give me a perimeter of 32 meters. And I'm going to start with the smallest possible width. So you can picture a rectangular enclosure with a 1 meter width and a 15 meter length. So that rectangle would look something like this. You can imagine that this would be a 1 meter width here, and I've got two 15 meter lengths. So if I add all those sides up to get the perimeter, that does give me 32. I've got two lengths, two widths. And to get the area of this rectangle, you'll recall area of a rectangle's length times width. So I just multiply these two together to get this value here. So that's one possible scenario where I would have 15 square meters of area. Now, this whole process of optimization, our goal is to find the greatest possible area. So you'll see that if I actually make some adjustments to the shape, you're actually going to end up with more area than if I had fixed dimensions of 1 in 15 meters. So my condition of perimeter is fixed. So I have to have 32 meters in this case. So what I want to do is investigate what other combinations are there for length and width that would still give me a perimeter of 32 meters. And by changing those dimensions, what happens to the area as a result? So let's look at the first one here. If I increase my width to 2, I need to consider what my length would be to still somehow get 32 meters of fencing. If I have two widths, I've got a width of 2 and a width of 2, that's 4. So I still need two lengths, and those have to be the same value. So you got to think, well, what number would the length then become if I got a width of 2? And if I have 14 and 14, that's 28. And if I add 2, that's 30. And another 2 would be 32. So that still satisfies my perimeter condition. But if we look at the area, length times width, you'll see that we actually end up with more area. So just by increasing the width to 2 meters, decreasing the length to 14 meters, I've actually increased my area almost by a factor of 2. So you're thinking, well, if this is the case, if I just increase my width, can't I just increase my width indefinitely? But you got to think, well, if I do that, if I make the width bigger and bigger, at some point the length will become smaller and smaller, and it'll turn into the same rectangle that we started with in our first row of our chart. There is an optimal set of dimensions that will give an optimal area, as in the greatest possible area. If we kind of just work our way through this chart, you'll see that we keep increasing the area that we get until a certain point. You'll see that we actually start decreasing our value for area. So you can see the difference here between 55 and 60. I went up by 5. All of a sudden, I'm going up by 3. I'm starting to decrease in the amount of area that I'm gaining. This was probably the smallest jump here, 63 to 64. I've only gained 1 square meter of area. So you can probably guess what's going to happen behind this box. Based on my chart, you'll start seeing some symmetry here. So I've got a 9.7 measurement and I've got a 7.9. You could probably guess that this is also going to be 63. Okay, so what happens is you get this increase in area until here, at which point the area then begins decreasing. Picture this as like the top of a mountain. This is the highest possible area for a 32 meter fence. So if I make a rectangular enclosure that is 8 meters by 8 meters in measurement, that would be a square. So it turns out that to get the most possible area out of a rectangle, you got to make that rectangle a square. Another kind of interesting example, this kind of showed up as a result of people trying to save money. If I want to build a fence and if I have a wall, if I somehow incorporate that wall into my enclosure, I can effectively cut down the amount of fence that I use because one side is made up by a pre-existing structure. So picture that I have like a barn and I'm building sort of like an enclosure around the barn. One side of that barn will make up a side of the enclosure, which therefore reduces my perimeter, but does not affect the area. That's what this problem's working with. We're still working with a fixed perimeter of 32 meters. We want to find the dimensions of fencing that'll maximize area. So again, we're making area the greatest possible, but that still gives a 32 meter perimeter. The smallest possible enclosure would have a width of 1 and a length of 30. Well, the fact of the matter is I only have one length now. My perimeter formula changes entirely. The perimeter of this rectangle would be only one length and two widths. So this would be the first scenario. My one length has to be 30 because my sides are 1 and 1. Now, because we want to maximize area, it makes sense to investigate what would happen if I increase the width, decrease the length a bit. Let's see what effect that has on the area. I can continue this. If I keep making these adjustments, I get more and more area. At one point, we stopped increasing, so we reached 128 meters squared, and then from there on, any further changes will actually decrease the area of this enclosure. So as it turns out, a width of 8 meters and a length of 16 meters would provide me with the greatest possible area for this rectangular enclosure. If we compare that to the last example, the greatest possible area was 64 meters squared. So in this case, if I get rid of one side of fencing, I can double the amount of area that I have possible to be formed by this fencing.
Now, if this video helped in any way, feel free to like and subscribe for more mathematical chaos. And as usual, thanks for watching.